All right, hello. Sorry about the delay here. Got everything up, right? Yep. Let's get the camera up. Ooh. Oh, let's put this away too. All right. So the new stuff we're doing now, we're starting toward this other aspect of calculus, which is this cumulative branch. And right now we're just sort of doing it through a geometric problem, which is finding these areas under a curve. So to start off the problem set today, I wanted to start with something simple and just start with, computing some sums, just so we know sort of what's going on with these. Just conceptually what they are. Oh, problem one. All right. So the first one, we have the sum from n equals 1 to 5 of 2i squared minus 1. I've mixed up n and I, haven't I? Cool. This is supposed to be an I down here. Sorry about that. So again, what we're doing with these sums is we have some expression in here, and just related to kind of that general stuff we were talking about in the lecture videos, this would be the AI for this problem. AI would be 2i squared minus 1. Right? So AI is just some function of I, basically. Right? So we're going to plug in, starting at I equals 1, we're just going to keep plugging in numbers for I. So 2 times 1 squared minus 1, plus, go to the next number, which is 2. 2 times 2 squared minus 1. Go to the next number, which is 3. 2 times 3 squared minus 1. Plus, go to the next number, 2 times 4 squared minus 1. And finally, the last number is 5, so we get to do one more. 2 times 5 squared minus 1. All right, and then just figure out what all of these are. So this is 2 minus 1. Plus, this is 2, 4, 8 minus 1. This is 18 minus 1. This is 32 minus 1. And last one, I'll just stick right here. This is going to be 50 minus 1. This is 1 plus 7 plus 17. Right? Yeah. Plus 31 plus 49. So this is 80, 88, 90, 105, I think. Right? So again, the most important part of this isn't, I don't care so much about the final number in the process. What I care about is understanding that this notation here means this process here, right? Where we just plug in the first number, then the next one, the next one, then the next one, then the next one, all the way up to whatever the top number is here. All right. So any questions about that one? All right, excellent. So I think what I'm going to do is I'll write the next problem here. And again, this should have been I equals 0 on the bottom. I from 0 to 3 of I cubed minus I plus 7. Go ahead and try this one out on your own real quick. See what you can get, and then we'll go through the solution in a minute here. let's see how you guys did. So again, here we're going to start at the bottom number, which in this case is 0. We start there and then we just plug these in. So plug in 0, and we have 0 cubed minus 0 plus 7. Next number is 1. 1 cubed minus 1 plus 7. Next number is 2. 2 cubed minus 2 plus 7. And finally, the last number, which is 3. 3 cubed minus 3, 7. So that will be 7 plus 7 again. Plus, this is 8 minus 2, which is 6. So it's 13. This is 27 minus 3, which is 24, plus 31. All right, so this will be 14, 27, 58. Right. And then that's it. So hopefully that's about what you guys have. Any questions on that one there? All right. So let's go ahead and do the last sum here. So here we have sum from I equals 3 to 8 of cosine pi I over 4. Right? So my point in this problem here is it doesn't always have to be some kind of polynomial expression for the AI. It can have exponentials in it, it can have trig functions in it, can have polynomials, it can have square roots, it can have basically anything you want, right? It's just some function of I. Right? So, but we follow the exact same rules when we do this. So we start here, the bottom number is 3. So we're going to start with I equals 3 and start moving up. So cosine, this will be 3 pi over 4 plus cosine 4 pi over 4 plus cosine 5 pi over 4. I'm right now wishing I hadn't picked such a high number. Cosine of 6 pi over 4. Cosine 7 pi over 4. And cosine 8 pi over 4. All right. And now we want to compute these. See, cosine of 3 pi over 4. Let's see, cosine is negative over there, so this is negative root 2 over 2. 4 pi over 4 is just pi, so this is negative 1. 5 pi over 4 is going to be the same as this. 6 pi over 4 is 3 pi over 2, so it's 0 there. 7 pi over 4, cosine is positive in the fourth quadrant, so this is just root 2 over 2. And 8 pi over 4 is 2, is 2 pi, so this is just 1. And now a bunch of things are going to cancel, right? So this 1 and the minus 1 cancel, this root 2 over 2 and the negative root 2 over 2 cancel, and so this is just negative root 2 over 2. Right? So point here was just, you can use anything you want and you just plug in the next number and then the next number and then the next number and you just add all these things up, right? Any questions? Really wish I could have this camera like right there, but there's a mounting bracket behind my monitor that doesn't allow it to be there, unfortunately. All right. So if there's no questions on that one, let's look at the next problem here. So the next problem, this is getting more toward the key part of the lectures for today, which are doing Riemann sums. right? In this case, we're just doing kind of small examples of them, you know, left endpoint, right endpoint, and midpoint rules, right? So in problem 2, what I really want to get at is, you know, let's look at these with precise examples and see what we can compute. Okay. So problem 2. All right. So here we're looking at the graph of f of x equals sine of x, and we're looking at it on the interval from 0 to pi over 2. Right? And we want to estimate the area underneath this, right, using 4 rectangles. All right. So let's sketch a graph real quick just to see what we're working with. So if this is pi over 2, and then 1 is up here, maybe we'll put, see, this is a half. So see, sine is a half at pi over 6. Probably somewhere around here. Right. So what we're asking in this question is we're trying to approximate this area. Right? We're trying to estimate that area there. All right. So we want to do this in, again, 3 ways: left endpoints, right endpoints, and the midpoint rule. Okay. So let's start by drawing a picture of what we're doing for this. Okay. So we'll start with left endpoints. Right. So left endpoints, we're going to divide our interval. We want 4 rectangles, so I'm going to divide the interval from 0 to pi over 2 into 4 pieces. Say here's 1 up here. Here is our sine function. Right. And let me just draw a red line here to say this is where we're ending it. All right. So what I want to do is I want to draw 4 rectangles in here. All right. So since we're using left endpoints first, I want to pick out all of the left endpoints of my intervals, which are here, 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 and here. Right. There's 4 intervals, and these purple dots here, these 4 dots, are the left endpoints of those intervals. So now I want to draw in my rectangles. Okay. So the first rectangle has height given by where I draw a line from the left endpoint, this dot right here, up to the function. Well, the function crosses the x-axis at that point, so it has height 0. So my first rectangle is actually just a flat line. Right? It has no area. Then I move on to the second dot. Right? So the second interval, here's my left endpoint. Draw a line all the way up to the function. Okay? And then I'm going to make a rectangle out of it that ends there. Right? So here is that rectangle. And then I do the same thing for the third interval. Start at the left endpoint. I draw this line all the way up to the function. Where it hits the function, I move over and then back down. All right. And one more time for the last interval here. Hit the function, move over, come down. Right. So all of these are left endpoint rectangles because the left edge of the rectangle hits the function, and that tells the rectangle where to stop. All right, so there's the picture. Now let's actually add up the areas of all of these rectangles. Right? So again, to get the width of these rectangles, to get this size right here, what is this width each time? Well, the width, again, is delta x, which is b minus a, the ending point minus the starting point, so pi over 2 minus 0, divided by however many rectangles we want. We want 4 rectangles. Actually, let me move this up here. Right? So maybe I'll just write here. Each of these have width delta x. Okay? So when I compute this, you're going to see a pi over 8, right? Because that's how wide these intervals are. So what I want to do, so now I know all of these rectangles have width pi over 8, right? And now I need to say how high each of these rectangles are, which means I need to know the y values at these 4 orange dots here. Right? And the y values of these are going to be, well, this is f of 0 down here. This one is f of, so when I move from 0, if I move by 1 delta x, I'm at pi over 8, right? When I go to the next one, this is going to be pi over 8 plus another pi over 8. That's pi over 4. Then finally, the last one here, this is going to be at pi of, 3 pi over 8. Right? Those numbers, plugging in 0, pi over 8, pi over 4, and 3 pi over 8, those are going to give me the heights of all of these rectangles. So, L4, maybe we'll kind of write this out explicitly once. It's going to be f of 0 times delta x. That's the area of this flat rectangle here. Then plus f of pi over 8 delta x, right? Plus f of pi over 4 delta x plus f of 3 pi over 8. Keep running out of room. Delta x. All right, so remember, L4 stands for the area estimate with left endpoints and 4 rectangles. Okay, so let's compute all these things. So this is sine of 0, because remember, f of x is sine of x in this problem. So sine of 0 we know is 0. Oh, sorry, I wanted to say one more thing. Because I was doing this in the video and it'll save us some time. So since there's a delta x in all of these, we may as well factor out the delta x. Wish the chat box on this. So calculating the y value, so that's what we're about to do. But the y values, again, since we're using left endpoints, we're looking at the left edge of each of these intervals. So these 4 points corresponding to these x values right here. If we take those and we plug them into the function, so in our case, we're going to plug all of these into sine of x. When we plug that x value into sine of x, that tells us how far up to move to the function. Or in the case that we have a function that dips below the x-axis, it tells us how far down to move. So the y values, or the heights of the rectangles, are always just plugging in the various x values into your function. That's always what it is. Right? Yeah, so y values, heights, always controlled by values of the function. Does that make sense? Or clear that up? Awesome. All right. So let's go ahead and actually compute these things now. All right. So f of 0 is 0. Oh, sine of pi over 8. Okay. I don't know how many of you remember how to do the half angle stuff by hand, but I wouldn't recommend it. So let me just pop that into Mathematica. Sine of pi over 8. Right. Okay. There is a nice closed form expression for this. Right, here we go. It's this doodad here. This is going to look a bit awkward, but it's root 2 minus root 2 over 2. All right. So this is something, let me point out, well, anytime you do something numerical like this, we'd probably be doing this on WebAssign at these days, or, you know, with the way things are going now. But you know, doing estimates like this would be fine to change this to a decimal. Like, you wouldn't have to worry about that. Right. I do like having exact answers as much as possible, but you know, this one's a bit of a weird looking one. Let's see. Sine of pi over 4 is root 2 over 2. And 3 pi over 8, I think we just switch it to a plus underneath that radical. Hey, I'm right. So 2 plus square root of 2 over 2. And then times delta x, so times pi over 8. Okay. So we need to compute all this stuff. All right. Well, that's going to add up to something fun, I'm sure. So let's find a decimal approximation of that at this point. There's not really anything good, so we'll plug this into a calculator here. Let's see, what are we going to get? Right. So this is going to be approximately 0.79. Let's do 3 decimals. Approximately 0.791 here. Right. Okay. Any questions about that one? All right. Cool. So let's do this again, but with right endpoints. Right? Again, just so we can sort of see the difference in all of these. So with right endpoints, right? Again, we're going to do basically the exact same procedure, but instead of using the left edge of the intervals, we're going to use the right edge. Now here, since we're using 4 intervals, we're going to have the same chopping up of the x-axis here. Right. Same thing, this is pi over 2. It's going to cut into 4 pieces. 1 is going to be up here. And sine is still going to do this. Right. But now, though, this time, those purple dots, instead of being on the left ends of all of these, they go on the right edges, right? And to get the height of the rectangles, again, we take these 4 dots, these 4 x values, and we plug them into the function to get our height. And plugging them into the function, that basically is just going to move us up to where the function is. So from here, we draw a line up, a line up, draw a line up, draw a line up. Right. So here, I'm going to draw this over and down, over and down, over and down, over and down. Right. So here we have our 4 rectangles with right endpoints. Because again, if you look at the right corner of each rectangle, the top right corner for each, I shouldn't say top right, but the right corner of each rectangle that touches the function, that's where the rectangle is sort of determined how tall it is. That was a bit of a word soup there. That's what determines how tall the rectangle is. Right? So R4 in this case, please change colors. Thank you. R4 in this case, right? So we need to take all of these right edges and plug those into the function and add those up. Right? So this is f of pi over 8 plus f of pi over 4 plus f of 3 pi over 4, or 3 pi over 8, plus f of pi over 2, and again times delta x, right? Because again, delta x is the width, and these are all of the different heights of the rectangles. And now we just have to add all this up. So let's see, this was the square root of 2 minus square root of 2 over 2. This one is root 2 over 2. This one is square root of 2 plus square root of 2. This one is 1. And times pi over 8. Right? So this is actually going to be this answer plus pi over 8. So we'll go ahead and run this through a calculator again, or Mathematica. Let's see here. Let's do that. So this one will be about 1.183. The right endpoints here. Right. Does that look good? Any questions about this one at all? All right, cool. So yeah, so again, the doing these things, it's not too bad once you kind of understand what the procedure is for these. Obviously, if you start doing things like with 8, 10, 12 rectangles, doing it by hand is going to get a bit more intense, right? Just a lot more computation. But this is, this is why we have Mathematica. And I did, in one of the lectures, we talked about, I had a code up there for how to do things like this in Mathematica, with some comments and a version without. And we'll use that actually for the next problem. But let's go ahead and do the midpoint rule one by hand, just to see it worked out, see the picture. Because I think it's always important to at least do 1 or 2 examples of this by hand on your own so you can sort of see it work out, right? So let's do the midpoint rule now. Okay. So midpoint rule here. I'm going to start off with the same picture. Pi over 2. We're still going to cut this into the same 4 pieces. This function still goes up to 1. Let's go away. Right. We still have our function here. We cut this off again. Now, the midpoint, right, it's basically exactly what it sounds like. If you understand left endpoint and you understand right endpoint, midpoint, it's exactly the same, right? So here, in each of these 4 intervals, actually I was using purple for this, in each of the 4 intervals, we're going to take the midpoint. Oh, this one, this one, this one, and this one. Now, I'm actually going to draw the lines up to the function in yellow this time, just to distinguish what's what here. So when I draw these lines up to the function, this tells me how tall the function is going to be, or the rectangle is going to be, right? And now let me actually draw the rectangles in green. So since this is how tall it is, I just draw a line through the from the start to the end. And there's my first rectangle. Okay. Here, let's draw second rectangle. Right? Draw up to the third spot. Here's our third rectangle. And draw up to the fourth one. Right. So those are our 4 rectangles in this case. Right, these 4. So if you look at it, the middle of the rectangle, the middle of the top of the rectangles hits the function each time, right? And that's why it's called the midpoint, right? Right. Any questions there? All right. So how do we compute this sort of thing? Well, call this one M4. All right, so it's going to be the same kind of deal. It's going to look exactly the same as the left endpoint stuff, the right endpoint stuff, except, the numbers on the inside of F change. So we have to figure out what are each of these values. So we know here, like this is pi over 8. This is pi over 4. This is 3 pi over 8. Those are the actual endpoints of the intervals. Oh, this one's 0, obviously. So what are these numbers in the middle? Well, take the average of 0 and pi over 8. So in the middle here, we have pi over 16. And the nice thing is, to get to the next midpoint, so to get from here to here, I just add delta x, right? That was the idea behind that, if you remember the xi stars from the videos. We just take the first one, whatever place we're starting at, and we keep adding xi star over and over, and that moves us from x0 to x1 to x2 to x3, and so on. So if we add pi over 8 here, maybe let me shift these values down a little bit. This will be pi over 16. That means this is going to be 3 pi over 16. This is going to be 5 pi over 16. And this is going to be 7 pi over 16. Right? Those are going to be the values that we plug in for the midpoints. Pi over 16. Pi, or 3 pi over 16. Pi looks horrible. 3 pi over 16 plus 5 pi over 16 plus f of 7 pi over 16, and then again times delta x, right? So now these numbers, they're going to be a little less nice. We can get these in terms of radicals, I'm sure, because 16 is a power of 2. But for example, we won't bother when doing this. Maybe we'll just write out here like this is sine of pi over 16 plus sine of 3 pi over 16 plus sine of 5 pi over 16 plus sine 7 pi over 16 times pi over 8. And then we'll toss this in Mathematica. But if anyone's curious, for example, sine of pi over 16 is square root of 2 minus square root of 2 plus square root of 2 over 2. If anyone happened to be interested in what that is. But, by no means am I expecting you to sort of write this. This is just calculator stuff at this point. Right? So, let's look at what this is. So this should be about 1.006. Right? So let's actually look at these three answers here that we have. Right? We have, for the left endpoints, we have, 0.791. For the right endpoints, we have 1.183. And for the midpoint, we have 1.006. So we get, the midpoint rule sits somewhere in the middle. The left and the right endpoints are drastically different answers, right? And if we look at the left endpoint stuff, in this case, this is a big underestimate, right? We get a big underestimate here because there's lots of gaps in that area that we're trying to compute here. Okay. We go to the right endpoints, we get a decent sized overestimate because we have all this overhang here, right? And then the midpoint rule kind of splits the difference, right? Each rectangle gives a little bit of overhang, but a little bit of gap. And so that overhang and gap there, they do a decent job of kind of averaging each other out, right? So I think I was saying I talked about this in one of the lecture videos, but out of these three, right, those of you who are watching, out of these three ways of estimating the area, which one do you think does the best job? Yeah, it's definitely the midpoint rule. Right? Now, eventually, let me point out, once we take huge amounts of rectangles, we're gonna get a good estimate no matter what method we use. But the point is the midpoint rule gets there way quicker than the other two. Right? So we'll see this again in a little bit. Right? But yeah, midpoint rule is by far, the best one here. And it's kind of funny, and this is sort of how real life things always work out. The easiest way to do something is usually the worst way to do it. Not always. But like here, we're trying to estimate stuff, so taking the easiest approach isn't the best. Right? But the more complicated approach gives us a better answer. So let's look at this with 50 rectangles. So that's problem 3. Right? So problem 3, we want to do this with 50 rectangles. So we want L50, we want R50, and we want M50. I'll do this on next line, I suppose. Right, I want each of these three numbers. Now, obviously, we're not going to do this by hand. So let me pop over here to Mathematica. Right. So I've been using this, of course, to do the computations. But so here, here's the version with comments. But I'm going to go down to the version without comments since I have the explanation of how this works. And here, we're trying to find the area under whatever function is here. This is our starting and our ending point. So in this case, 0 to pi over 2. All right. N is the number of rectangles. So here, let me change that to 50. Right. This line we don't have to change. This is the width of the rectangles. And this extra line down here I added so it always spits out a decimal. Right? So the thing that you really have to change, the three things you'll have to change when working with this code, and I did post this on Notebowl, so there's a, somewhere in the Documents tab, there's this Riemann sums document, right? And yeah, so the only things you really have to change are these four and this spot right here, right? So again, if we want left endpoints, so this is where you have to go back to that video where I was kind of speaking very generally about what the rules look like, right? This is the xi star line. So if we want left endpoints, we have to use this. And that's because our sum starts at 1, but we need x1 star to just be a. So we have to make sure we get 0 copies of delta x. So when we do this one, when we run this one, we're going to get 50 rectangles. Now it's not going to graph it, of course, but go ahead and see it. So this is the exact answer. You probably don't want that, which is why I put this extra line here with the n. Another option, by the way, if you wanted to force decimals is, I think if you put a decimal here, Mathematica is going to use its sort of decimal in, decimal out philosophy. Right? But if you don't do that, which is fine, you're going to get this, but if you use this n command here, it's going to also spit out the actual decimal. Another option, if you don't remember this, for example, if you forget that you can do that, you run it and you get this hideous mess. Let's see. There's usually... where'd it go? Okay, there's usually that's what I want. Oh. Okay, I don't know where it went. There's usually a thing down here for finding an approximation. All right, well, sorry about that. Let's hopefully remember the n. Right. So that's going to give us this, 0.98421. All right, actually, let me keep with the 3 decimal thing here. All right. And, all right, so the next thing I want is I want right endpoints. So if I want right endpoints, I can just, here, I actually do want to start with a plus delta x, right? I want to start at x1. So I just have k. Make sure there's a space here, right? If we don't have a space, you're going to run into this problem where everything is blue. Make sure there's a space between the k and the delta x. very important. A way to sort of make sure you've done that is keep the parentheses around the k. That'll be perfectly fine as well. Right. So run that, and we'll find that the 50 rectangle right endpoint approximation is 1.01563. 1.016 if we use 3 decimals. All right. Now, lastly, the midpoint rule. Midpoint rule, we just split the difference. So again, if this were left endpoints, we had k minus 1. If it were right endpoints, we just have k. When we want the midpoint, we just go halfway between that. So minus 0.5. That wasn't a point. Minus 0.5. Or k minus a half. But if you use the 0.5, you're going to get the decimal that you want. So let's go ahead and do that. So 1.00, well, 0. That's what it rounds to with 3 decimals. Right? So hopefully that's not too bad there. Right? Any questions about this one here? Go ahead and switch back over to what I've written down here. Any questions so far? So, all right. So the last question here is problem 4. And the question was, well, what do you think the exact area is? How do you think we could compute such a thing? Well, we can see that by increasing the number of rectangles we use, we're going to get better and better estimates, right? In fact, let me even ask, what do you think the actual area under this curve is going to be? Right, so here's the 4 rectangle numbers. Here's the 50 rectangle numbers. What do you think the actual area from 0 to pi over 2 is? These give any kind of hint? Yeah, so it actually is 1. Right? So the way we can do it, I also want to point out here, as additional sort of evidence that the midpoint rule is way better. Here, let's look, when we did just 4 rectangles, the midpoint rule was correct to the second decimal place already, right? These ones are correct to no decimal places. They're not, atrociously far, but they're correct to like no decimal places at all. Right? We move over here. This one has 1 correct decimal place, the right endpoint. Left endpoint, it's getting better, but it's not quite there. In fact, we can count the 9 as a correct decimal place. Because if we had 0.9999, like infinitely many 9s, that is 1. So we'll say this has 1 correct decimal place. But now, the midpoint rule actually has 4 correct decimal places. So how could we do this, though? How could we compute the actual area? Well, if I go back to Mathematica here, right? If instead of saying what n is, maybe I get rid of this line. Let me get rid of this as well. Right, so I'm not going to specify n. So when I run this Riemann sum, okay, it's going to spit this thing out. But that's fine. It's going to spit out this expression here. And then if I keep pushing the number of these rectangles infinitely high, so if I take the limit of this thing as n goes to infinity, is this going to work? Yeah. So we get 1. Maybe here, let me say, you know, if we just take a limit of this thing, this is always going to approach what the actual area should be. And the nice thing is it doesn't matter if we use the midpoints like here, if we change it to the left endpoints, right? This maybe actually looks a little better than that, but it still converges to 1. If I change this to right endpoints, that's even better, and it still converges to 1. So the nice thing is, like I said, at the end of the day, no matter what method we use, it's always going to push off to the correct area. So the answer to this would be basically take the limit as n goes to infinity. And the exact area is 1. All right. So the next set of lecture videos, which I'll be working on sort of this weekend here, get those up for you to watch on Sunday. But these, yeah, so that'll be sort of the theme, is how do we start moving from these approximations that we were doing off to the actual exact areas. All right. So that's it for the problems today. I know we spent a bunch of time on really one example here, but that's sort of the theme, or the main point is we just want to be able to understand how that example works. Yeah. So I'm going to send out some information soon about exams, like how we're going to kind of handle that. I think I have an idea what I'm going to do for exam 3. The final, I'm still kind of thinking through. I want to, treat that a bit more carefully. But I think the idea for exam 3 is going to be something like doing a few, like a series of little timed quizzes on WebAssign, where you'll have to do it by a certain time, but like from the moment you open it, you'll have, say, 30 minutes to do that little chunk of problems. And I plan to do something where like you'll get a few attempts at each problem. Probably not the usual 100 for the homework. And it'll be something where like, each attempt, each wrong attempt might dock a little bit of points from that particular problem. And then like if you've attempted it, hopefully, I think WebAssign has this, where if you at least attempt it, you get something. I need to look into exactly what the details of that are. But the exam 3 will probably be made up out of that. And I want to, set it to do the scoring like that, so there's some form of partial credit. That way it's not just, like all or nothing. And then the final will probably have some questions with that style as well, like maybe half of the final or something like that. Maybe a bit less than half. But I'll also, one idea that I'm trying to think of, are trying to see if this will work. But there's a lot of students, so we'll see if we can actually get this to work. But one thing that would be neat is to sort of have like one-on-one sessions here in Google Meet where I ask you to, talk through a problem or two, just so I can sort of check conceptual understanding as well. But again, these are trying to figure out how to do a meaningful exam, through distance learning is actually a bigger challenge than I was expecting. I should say, like, I didn't think it would be easy, but it's actually a lot trickier than I thought. But yeah. So on that note, though, any questions at all before we head out for the day? Good. All right. All right. Well, with that, have a great weekend, everyone. And I'll see you on Monday for more Riemann sums and then actual integration. Oh, have a good weekend. Take care. Be safe.